So we're going to take a look at the last section of Chapter 3, which is all about second-order linear equations. So we've seen second-order linear equations up to this point, and in Chapter 2, the end of Chapter 2, we learned how to kind of convert convert these second-order systems into first-order linear systems. We just have to make a presumption. So here's an example of a second-order differential equation in terms of y. Hold on, let me turn off the autofocus so it doesn't keep doing that. We have to make a presumption, and so we're going to presume, based on this kind of second derivative right here, that dy dt is going to be equal to something that we're going to call v. Now, we can make that assumption and proceed and solve as necessary. The only problem is this is only in terms of one dependent variable. So if we do make that assumption, we're going to kind of base it off of this idea here that this is the derivative of y, or excuse me, the derivative of v, right? And so this thing right here, which we can let be represented by v. So we're making this presumption, but in the end, it's important to note that by converting it into a first-order linear system, we really only can use the y of t solution, right? The v of t solution depends on y of t in terms of it's the derivative of the y of t. So this is the only thing that would be useful from this method. So given a second order differential equation, we can make a presumption and then proceed, but in the end only the y of t, only the actual solution y of t is going to become useful and necessary for us. So for part A, it says convert the equation into a first order. Well, the first equation that we know for sure is dy dt equals v. The second equation that we know comes from this, which we can do a little bit of manipulating and say, well, that's v prime, that's dv dt. And that's equal to, if I move these two other terms to the other side, we're going to have a negative 10y minus 7v, which of course we can rewrite as a matrix equation, right? This could be rewritten as dy dt and dv dt is going to be equal to our coefficient matrix. Now we got to be careful. Our coefficient matrix is going to be y term first. So in that first equation there's 0 for the y term and 1 for the v term. The bottom equation is negative 10 and negative 7. And that of course is times our two dependent variables. The first one that we were given to begin with, the second one that we kind of invented with our presumption. So this is a perfectly reasonable representation of the same information here with a presumption along the way. So we can proceed and solve this. We know how to do that with a little bit of effort. We just need to figure out how to solve it by finding its eigenvalues and eigenvectors. So eigenvalues and eigenvectors is the next part. Oops, let me scoot up a little bit. And so for the eigenvalues and eigenvectors, I'm going to set up my equation. So it'll be 0 minus lambda times negative 7 minus lambda minus negative 10 times 1. So minus a negative 10 equals 0. With a little bit of effort, we find that we have lambda squared. Middle term is going to be plus 7 lambda, and then our last term is plus 10. Now if you're paying attention and you notice, hey, this looks really familiar, those are the same coefficients, 1, 7, 10. Those are the same coefficients that we started with, 1, 7, and 10. There's a very good reason for that, and it's what we run into before, and I'm just going to write 1 here. That the 1, 7, and 10 that are up here appear here as 1, 7, and 10. So if we wanted to, we could just kind of jump right to this step right here. We didn't have to go through all that rigmarole. But proving where it comes from is important. Of course, this thing does factor it factors into lambda 1 equals -5 and lambda 2 equals -2. Now, we can go through the process, or we can just hop on Maple and find out what V1 and V2 are going to be equal to. So I'm just going to kind of cut to the chase for this one because we've done enough of these problems where we figure out what our eigenvectors are. And the eigenvector associated with -5 is equivalent to -1, 5. And the eigenvector for this guy is 1 and 2. And again, we can find those on Maple, or we can do it by hand the long way. Either way, you're going to figure it out. So we have our eigenvectors and our eigenvalues, which means that I can do part C, which is all about writing the general solution for the system. So let me scoot this up a little bit further. Sorry, these papers keep sticking on this board here. So we know that our general solution in matrix form is going to be a combination of our straight line solutions that we get from lambdas and v's over here. So k1 times e to the -5t times its eigenvector plus k2 times e to the -2t times its eigenvector. Oh, whoops, I think that's supposed to be a -2. Yeah, that's supposed to be a -2. This one right here. Boop. So, boop. And so this is the general solution for the system, but this is not the solution for the original equation that we came up with. The general solution for the initial equation that we came up with is really only the y of t part of it. Sorry, the little y of t part of it. So if you think of this thing as being able to be written in parametric form, we'd have y of t and v of t equations, right, collectively. And so the first equation, k1 e to the, oops, sorry, with a negative in front of it because the -1, to the -5t plus k2 e to the -2t. That's the position equation, y of t. And if you take its derivative, you can probably see where it's going. The -5 times the -1 becomes 5k1 e to the -5t minus 2k2 e to the -2t. And you can see that the velocity really is just the first derivative of the position. But technically, only this equation right here, this is the general solution for the second order differential equation that we started with at the top. Whereas this right here, this is the general solution for the system. So if you were asked to find the general solution for this equation right here, saying this really is not correct. The solution is just this right here. Y of t equals k1 e to the -5t plus k2 e to the -2t. And the reason, or the way you can see that is if you go into Maple and you were to type desolve this guy right here, if you were to try to desolve it, it would only spit out a y of t, right? Because the solution for this is y of t equals some function. Now, given that we can turn a second order into a system, into a matrix, we can solve it using our eigenvalue, eigenvector technique. But we have to kind of throw away the second part. If you really want to know what the solution is, it's just the y of t. That becomes particularly useful. The other thing to pay attention to on this page, and I'm just going to add a little note at the bottom, is you probably recognize that the 1 lambda squared plus 7 lambda plus 10, that corresponds to the 1 d2y dt squared plus 7 dy dt plus 10y. And you probably recognize that this 1 corresponds to that 1, and this 7 corresponds to that 7, and this 10 corresponds to that 10. And so we kind of didn't need to go through all the process of turning it into a system. We could have just jumped right into this characteristic polynomial. In fact, that is often what people will do when faced with a second-order differential equation like the one up above, right? You just say, oh, look at the coefficients and turn it into the particular characteristic polynomial and then proceed from there, right? You can find the eigenvalues and go from there. But we're actually going to tie it, we're going to connect it to a method of solution from before. So on the next page, we can solve that exact same second order system, but using the lucky guess method. And if you remember from before, the lucky guess method said, if we're able to guess what a solution looks like, a generic solution. So for example, if we have something like y equals e to the st, that means our y prime, if you take the derivative of that, should be s e, that's not 5, that's s, e to the st. And the second derivative would be s squared e to the st. Right? So we have our first derivative and second derivative based on our guess. If this is our guess, right, that's our y of t. If that's true, then we should be able to substitute that back into our second order differential equation. That means my second derivative, d2y dt squared, so s squared e to the st plus 7 times s e to the st plus 10 times the original guess, e to the st, must be equal to 0. And of course, we can cancel that out. This must be true for some s value. That has to be true. And so if you do a little bit of canceling, you can see I can factor out e to the st, and those just become 1 when I cancel them out. Because of course e to the st can't equal 0, so I don't have to worry about dividing it away. And I'm left with s squared, or 1s squared, plus 7s plus 10 equals 0, which is exactly what we saw before, the same as the characteristic polynomial. That really is the same thing. It's the same as the characteristic polynomial. So what do I do from here? Well, I just proceed, solve for it, and come up with my two particular solutions. And this, of course, we know factors into s plus 2 times s plus 5, which means there's two possible solutions. One of them is s equals negative 2. The other is s equals negative 5. And that should look pretty familiar. Those are exactly the same as the eigenvalues. Right? So now we basically have our eigenvalues, and that means that we have our eigenvectors, that means that we have our two particular solutions. So we now have, we know two particular solutions. And those two particular solutions are y of t equals e to the negative 2t, and y of t, call this one y1 and y2, equals e to the negative 5t. Those are particular solutions. Now notice, there's no constant sitting in front of them, because that by itself, if I plug it back into the original differential equation up here, that would make it true. So would this one. Right? So these are particular solutions that are 100% correct. Now what I can do with those is use those two particular solutions to get the general solution. And so if you know your two particular solutions, I can write my general solution Notice, not as a vector, but as the equation y of t is equal to constant 1 times e to the minus 2t plus constant 2 times e to the minus 5t. Now you might be looking at that and go, wait a minute, that looks really, really familiar. That looks almost exactly the same as what I had on the previous page. This is the general solution for that second order differential equation. Just remember though, on the previous page, our general solution looked like this: negative k1 e to the minus 5t, positive k2 e to the negative 2t. But hopefully you can see that negative k1 could be just, you've pulled the negative inside the constant. It's a constant. It could be positive, it could be negative. It's whatever we need it to be, right? So this really is fundamentally, functionally the same. And the other thing that's kind of worthwhile noting here, that means that we can calculate v of t by just taking its derivative. The derivative of this becomes negative 2 k1 e to the minus 2t minus 5 k2 e to the minus 5t. And the relationship between y and v is exactly the same here as it was on the previous page, right? The relationship is exactly the same. The signs are opposite for each one of these two terms, and the value of k becomes 5 times bigger, becomes 2 times bigger for the velocity. So we get the exact same result. How does this compare? Well, this scalar solution is, personally, I think it's easier to get to. So we don't have to mess around with turning everything into matrices. We can just use this trick, use this lucky guess trick. So at the bottom of this page, you'll see it kind of spells out when do you use which form. If you want to calculate formulas to use, like making specific predictions about position or velocity. Specific predictions, that means we're doing quantitative analysis. If you're doing quantitative analysis, you're going to use the scalar form, right? And remember, the scalar form, that's what we had called in the past the parametric form, because it gives you the y of t and the v of t in this case, right? If you want to make a prediction about general behavior, especially on the phase plane, if you're interested in behavior, then you're talking about qualitative prediction. Then you're better off using the vector form. And in the vector form, of course, we mean the matrix form, because you can tell what the straight line solutions are. You can tell what direction things are moving on the phase plane. You can tell whether things are, the origin is a source or a sink. You can make all kinds of predictions qualitatively about what's going on. Okay, so that gets us through the first 2 pages. There's one more page left in this section, and we'll have that in another video.